On this video, going to pick up with the idea of average rate of change and also take a look at some of the algebra involved in the difference quotient. So it's a continuation of the last video. So I'm going to look specifically at this function here, y equals g of x, 2x cubed minus x. So for any particular input x, you cube that, multiply it by 2, and subtract the input to get the corresponding y value or output. We're going to look at the average rate of change. Now, the average rate of change is an average. It depends very much on which points you're looking at. So for this particular function, I would get a different average rate of change if I used, look at the average rate of change from the point x equals 1 to the point x equals 10 versus looking at from x equals 2 to x equals 5, which is what we're going to look at here. So it's between x equals 2 and x equals 5, or on the interval from 2 to 5. Whether you think of it as an open interval like I have written here, parenthesis, left paren, 2, 5, right paren, 2, 5 in parentheses. That means all the numbers from 2 to 5, not including 2 and 5. I could have made it the closed interval from 2 to 5. Doesn't make any real difference, not important, at least not to me right now. So at some other context, some other class, some other time might be very important. Okay, so average rate of change. So what we mean by this is if we were to look at, let's look at a different window here. So the green curve here is that cubic function we started with, y equals 2x cubed minus x. Can't really tell it's a cubic function from the picture we've got here. Could just as well be a parabola or maybe some sort of exponential function. But if we could see more of it, we'd see that it looks like it could be a cubic function anyway. It's not always possible to tell the distinction between a third degree function or a fifth degree function in terms of polynomials. So. Okay, so the 2 points that we're looking at, so between x equals 2 back here, actually at 2.01, 14.2, but real close to the point on the curve here for x equals 2. And then for x equals 5, we're out here at approximately, actually got 2 different points there for B and C there. Actually, I don't know where point B is. Point B is off the picture, doesn't matter. Okay. Point C is the one over there, 4.99, real close to 5, and 244.13. The actual y value is 245, as we'll see here in a moment. So what the average rate of change is it's looking at, if you were to go ahead and draw a line through the curve, through those 2 points, what would the slope of that line be? So the average rate of change in the case of a line is simply the slope. The average rate of change in any other function is the slope of the line passing through 2 points on the curve, which is the graph of that function. Okay, so going back to our previous window here. Let's see, where is that? There we go. No, that's not it. Oh, there it is. Okay. So we're looking between x equals 2 and x equals 5. Well, it's really quite simple. You just go ahead and find the y values that correspond to those 2 x values by plugging 2 into this function, finding g of 2, finding g of 5. I did that in the opposite order here. G of 5 is 2 times the cube of 5 minus 5. 5 cubed is 125. 2 times that is 250. Subtract 5, you get 245. G of 2 in a similar sort of way turns out to be 14. 2 cubed is 8. 2 times that is 16. Subtract 2, we get 14. The average rate of change is the difference of the y values, 245 minus 14, divided by the corresponding difference of the x values, as we see here. Move the table out of there for now. Okay, so Here's the average rate of change, difference of the y values correspond and divided by the corresponding difference of the x values. 245 minus 14 is the difference of the y values, or 231. The x values had a difference of 3. 231 divided by 3 is 77. So the 77 is the slope of that line we're looking at. It didn't look all that steep, but that has to do with the perspective of the window. Had the window set up so that the x values were going from basically from 0 to 5, maybe 2 to 5, whereas the y values were going from down around 10 all the way up to about 250. So that's going to cause the window to look the way it looks. Now, what does that 77 mean? Why is that an average? Why do we call this the average rate of change? Well, if you were to go ahead and put together a table of values here, let's suppose we were just go ahead and look at x values of 2, 3, 4, and 5. So I just chose the integer values on the particular interval we're looking at. The corresponding y values are here, 14, which we calculated before. G of 3 is 51. G of 4 is 124. G of 5, as we did already calculated, is 245. If you look at the differences of just those, the change in y from 14 to 51, well, 51 is 37 more than 14. 124 is 73 more than 51. 245 is 121 more than 124. And there is some meaning to the pattern here, but we won't go into that right now. If you were to add these three numbers together and divide the whole thing by 3, because there are 3 numbers, it turns out the average of these 3 numbers is the 77 that we get up here. 121, well, let's add 37 and 73 together. That adds up to be 110. 110 plus 121 is 231. 231 divided by 3 is 77. So in that sense, it's perfectly reasonable. We call this the average. Question might occur to you, well, suppose we picked more values in this range between 2 and 5. Suppose we went from 2 to 2.5, and from 2.5 to 3, and from 3 to 3.5, and from 3.5 to 4, and from 4 to 4.5, and from 4.5 to 5. And so that we had more jumps. How would the average work out there? I'll leave you to maybe investigate that and see what you get. Okay, so that's the average rate of change. It's pretty straightforward. It's just the slope of a line passing through those 2 points. So as long as you understand the definition, it's pretty easy to calculate. So make sure you understand what average rate of change means. The difference quotient, as I mentioned in the last video, turns out is exactly the same idea with a different notation. If we're in calculus, it turns out that if you wanted to use the average rate of change and generalize that slope idea, which is what's the average rate of change is all about, generalize that so you could apply it to a function like the one we did here. Sometimes it'd be kind of complicated to talk about it. What we'd have to do is talk about 2 points getting close to each other. Generally, you would freeze one point and then let the other point get closer and closer and closer. And it's just more convenient sometimes to just say that the difference between those points is going to 0. That's the h here, as talked about last time. H is the difference of the x coordinates. And the numerator here, g of x plus h, and minus g of x, that's the difference of the corresponding y values or y coordinates. So what we have here, so I could go ahead and type this out using math type. It would certainly be a lot neater, but I will go ahead and we'll look at our function and see how to do the algebra here, working it out on the whiteboard. So again, our function is 2x cubed plus, 2x cubed minus x. Change the screen share here to the whiteboard. And then we'll go ahead and look at the algebra involved here. What happened to my whiteboard? Okay, so hopefully you guys are seeing the whiteboard. I'll have to do some editing on this video. Okay, I want to change my colors here to a plain old basic black. So first I'm going to calculate g of x plus h. So that's equal to 2 times the cube of x plus h minus x plus h. And of course, you recognize that the parentheses around the x plus h in both cases here are absolutely necessary for the correct order of operations. So don't form the habit of getting sloppy and leaving things out like parentheses. Often people will look at this and say, well, I know what's going on here. I won't bother with the parentheses. And that sort of sloppy habit will cause you trouble in the long run. So we have here, so keep in mind that if you cube x plus h, you do not get x cubed plus h cubed. It'd be nice if you could just distribute the exponent that way, but it doesn't work that way. So what we're looking at is x plus h times x plus h times x plus h. So what it means to cube something. Multiply 3 of those, 3 copies of that same thing all together. So you have that minus x plus h. Now there actually is a formula for the cube of a binomial. X plus h has 2 terms, so we can say it's the 3rd power cube of a binomial. And I could actually do this from memory, but let's go ahead and carry out some of the algebra. So if you wanted to raise x plus h to the 3rd power, you'd have to start by squaring it. So you pick 2 of these and multiply them together. It doesn't really matter which 2. Let's say we take the last 2 and multiply them together. So we'd have x plus h times the product of x plus h with itself, or the square of x plus h. So you can have x times x squared, x times h, xh, or the other way around, doesn't matter, plus h times x, hx, plus h squared. And we still have that minus x plus h. And again, write all this stuff down when you're doing this. Don't develop bad habits that you have to unlearn later on to make sure you don't make mistakes that are created by those bad habits. Okay, I'm going to go ahead and simplify the parentheses around the x squared plus xh plus h squared before I do anything else here. So 2 times x plus h times x squared plus 2 times xh plus h squared, and still minus that x plus h. It's tempting to not bother to write it and deal with it later on, but aside from the fact that I'd be writing down nonsense, there's also very real danger to forget about the fact that I didn't write something down. So don't try to just think your way through this without writing it down correctly. Okay. So let's see, I think I'll go ahead and distribute. Well, I'll keep the 2 outside for now. Okay, so if we had x times x squared, that's x cubed. X times 2xh, 2x squared h, x times h squared, h cubed. So I'm just using the extension of what people typically call FOIL, the distributive property, to multiply x plus h times x squared plus 2xh plus h squared. So I've completed the multiplication by x. Let's see, no, I didn't. Lost my train of thought here someplace. Okay, so we've got x times 2xh and then x times h squared, so it'll be x h squared. Okay, now I need to multiply through by h, everything. So h times x squared, so we have plus x squared h. H times 2xh would be 2xh squared, and then h times h squared, which is h cubed. All that still has to be multiplied by 2, and then we're going to subtract the x plus h. Oh, okay, so what can I say? We've got 2x squared h and 2xh squared. So yeah, it looks like we got 3 of each of those. So 2 times x cubed plus 2x squared, actually it's 3. X squared h plus 3 xh squared plus h cubed minus x plus h. And so all of that is 2x cubed plus 6 x squared h plus 6 xh squared plus 2 times h cubed minus x minus h. We don't have any like terms here. The first 4 terms are all, in a certain sense, cubic terms if we think of h as a variable, which really probably shouldn't. And then the last 2 terms are linear first degree terms. Okay, so we got 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus x minus h. And all of that again is just g of x plus h. So we have to take all of that stuff and take it to the next stage of calculating this difference quotient. So if we calculate the numerator of our difference quotient, that's g of x plus h. This is what it is we just worked out, minus g of x. That's equal to, so all the stuff I had just written out here was 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus x minus h. And then from that we would subtract g of x. Well, g of x was simply 2x cubed minus x. Well, if you do the subtraction here, we have 2x cubed minus 2x cubed, so those disappear. And then we have negative x, okay, right here, minus negative x. So those also cancel out. So it turns out that the terms that did not involve h disappear here in the numerator, and so g of x plus h minus g of x, so again this is the numerator of our difference quotient. Well, that's going to turn out to be simply 6x squared h plus 6xh squared plus 2h cubed minus h. And then keep in mind that the two terms in parentheses at the very end there, they were subtracted from equivalent terms we got from the g of x plus h, and so they are gone. So we just have these four terms. So now we're in a position where we can actually evaluate the difference quotient, I believe. If I can put it all on the screen here. So we have here is the difference quotient is g evaluated at x plus h, the function value at x plus h, minus the function value as given at x, and the whole thing is divided by h. And again, the numerator is the difference of two y values. The denominator is the difference of two x values. Okay, well, these four terms that we just worked out are the numerator is the numerator of the difference quotient. So we have 6x squared h plus 6x h squared plus 2h cubed I think get that exponent to where I am satisfied with it. Okay, minus h all over h. Okay, so what happens with division, which is what fractions are all about, dividing by h is possible. If you divide a polynomial by h, you can divide term by term, which is handy here because each term involves h. So the h's will be divided out here. So we would end up with 6x squared. H divided by h is gone, so don't have that. We'd have 6x h squared divided by h, so that's going to turn out to be 6xh. We would have plus 2h cubed divided by h, so that's going to be 2. H cubed divided by h would be h squared. And at the very end, we would have minus 1, which comes from the h divided by h. That's the difference quotient in this particular case once it's been simplified. Now that's the starting point of calculus, and in calculus what they would do with this is then take the limit of that expression, the g of x plus h minus g of x all over h, the difference quotient, take the limit of that by letting h go to 0. You can't let h go to 0 back when it's written out like this, because if h were 0, we would have g of x minus g of x in the numerator, which is g of x minus g of x is 0. If h is 0, then g of x plus h would be just g of x. So 0 minus g of x minus g of x in the numerator would be 0. The denominator would also be 0 if h were 0, and then you'd have 0 divided by 0, which is not an acceptable mathematical expression. We don't know what that means, if anything. However, once we've done the simplification, then we go ahead and assume that, well, okay, now I think it's going to be okay to let h go to 0. If h were to go to 0, the two terms involving h would actually disappear. And so the derivative of the function, this isn't calculus, so we don't necessarily care about the derivative, but if we did want to do the calculus, it turns out the derivative is simply 6x squared minus 1. If you've seen any calculus, then you may already have known how to find the derivative of 2x cubed minus x, and that it's actually pretty easy to do. But if you take calculus, you're going to be spending some quality time at the beginning days doing the sort of thing we just looked at here, understanding how the difference quotient can be used to find the derivative. Okay, so every sort of function has its own little tricks to it. So this is not comprehensive about all the things that you need to know about working with the difference quotient. But I don't want to make a 3-hour video to look at all the different possibilities for all the different sorts of functions, even if we restricted it to just polynomial functions and power functions and logarithmic functions and exponential functions, the sorts of things we see in college algebra, we'd still have a lot of work to do. So we'll have to leave it at this. So that's this video, and the next video I think it's probably time to look at composition of functions.